Okay, so in this video we're going to start talking about differential gain. Now this isn't necessarily the final quote gain equation we're going to be at here. We're going to have lots of different gain equations. We're going to have an open loop gain equation, but we're also going to have what we call a differential gain equation here. And so let's first off remember here that we have a VC1 and VC2. So why don't I go ahead, let me see if what's under, nope, that's not what I want, that's a YouTube video. I was seeing if I still had the circuit diagram in my clipboard, which instead what I had was a YouTube video that I tried to link in there, which we don't want. So let me just quickly sketch here. I'm trying to sketch this quickly and it's looking horrible. I'm not even going to sketch everything in here. So V plus, V minus, RC, RC, VB1, VB2, and then this is VC1, VC2. Okay, so that's just kind of a quick sketch of what we have here. Now remember here, what we are going to kind of define here is that there's more than one way we can define an output here, but we're going to define the output as VC2 minus VC1. And this is what we refer to as a two-sided output. And of course we refer to it as a two-sided output because, well, there are two sides. Well, this isn't too complicated to get to us here. So let's see here, what would we have here? Well, we'd have that V out is going to be equal to IQ over 2 plus let me get this going here again. V plus minus IC2 RC minus V plus minus IC1 RC, which real quickly we can see what happens here. These V pluses cancel. I've got a minus here, a minus minus, so this becomes IC1 minus IC2 RC. And now we're going to use not the equations with the IS and everything. I mean, we could do that, but remember how we talked about in our previous lessons? What we're going to do is we're going to try and do a way without having to use the exponentials. Because if we have to use the exponentials, life becomes difficult for us. So what we're going to do here is we're going to say that V out is equal to, well, I'm going to have this here. I'm going to put a big square bracket here. IC1, which is going to be IQ over 2 plus that delta I business, because we're saying that the difference voltage is going to be small. That VD is going to be small. Minus, and then it would be this IQ over 2 minus this delta I times RC. Okay, but let's think about this here. Let's go back to this graph here. This graph here, I'm going to blow up one portion of it here. And I'm just going to blow up that boxed portion. So and this isn't the 0. The 0 is going to be somewhere down here. And this, remember, was kind of my IQ over 2. And we said that these here had slopes, and these were transconductances. Now, we have to be careful. These transconductances here, these slopes, remember, it's the derivative of IC1 with respect to VD. But that was just this, what we called forward transconductance. But then the slope of this one here would just be the derivative of IC2 over VD, which would just be negative G sub F. Because remember we said, so what is being called, we're in the linear region here. And just to kind of keep having conversation go back to what we were originally trying to do here, is we're trying to build an op-amp. And remember, one of the things we assume for an op-amp is that the positive and negative terminals in an ideal op-amp are at the same voltage. And technically they're not, right? But let's look here. Well, in order for us to have this linear portion here, this VD has to be pretty small. So we're going to be wanting to stay in this linear portion, so VD is going to need to be small. So in other words, the difference between the voltages at the positive and negative terminals is going to be small, and especially when we add in feedback, it's going to be small to the point that it is negligible for what I would consider as back of the envelope computations. For more detailed analysis, of course, we'd go to a simulator. Alright, so then let's go ahead and figure out here, well, what's delta I? Well, I've got some VD that's being applied here. So, but now let's think about this here. This here is 0 volts. And this, for instance, I'll just make this spot right here VD. So this distance right here, I'll say my delta V. My delta V is simply just VD. Actually, I'm going to go up to this line here. But then if I look here, this is my delta I. But then what would my delta I be? My delta I would simply be, well, this is just a straight line. This would just be my slope, which is GF, times VD. Okay, but then remember, what did we say that GF was? We said that we could write an equation and get that GF was 1/2 GM. Because again, what were we doing is, well, we evaluated the slope at this point right here. And, you know, again, we're in these, quote, linear portions, and so it was just 1/2 GM. So now we're going to go back to this equation here. Let me go ahead and lasso this equation here. Copy that equation. Paste it right here. Okay, so this is my V out equation. But then what do we have here? Delta, whoops, I'm back in lasso mode. We have delta ID and GF is 1/2 GM. So what do we get? Delta I is equal to 1/2 GM VD. Okay, so then we plug that in. So we have V out is equal to IQ over 2 plus 1/2 GM VD, because that's my delta I, minus IQ over 2 minus, well, delta I is still the same thing, 1/2 GM VD. And this is all times RC. And clearly we can see some things. That cancels, being careful of the double negative, those become pluses. And we get then that V out is equal to, and I think this is so cool, GM VD RC. So what are we amplifying here? And this should look pretty similar to us here if we think about a voltage gain here. If we think about the differential voltage gain being V out over the differential voltage, we get that this is GM RC. And you should say, hey, this actually looks pretty familiar to me. This looks like what we would have for the this is what we had for like common emitter amplifiers. I know there's a negative in there, or common base if you want to have it being the positive here. But what does this give me here? Well, this also gives me here that another way to write this is that it is IQ, whatever your bias current is, times RC over 2 VT. Okay. Now, the problem here is that if often neither VC1 or VC2 is at ground. And so we're taking an output voltage as a difference between two voltages, which it's not bad, but what we often do here is we often will do what's called a one-sided output. And if we do a one-sided output, so this here, let me emphasize, this is for a two-sided output. But if we do a one-sided output, VC1 or maybe VC2, my differential voltage gain, I'm not going to go through the derivations. You can go through the similar kind of derivation as we just did here, but you're going to wind up with GM RC over 2, which is just going to be IQ RC over 4 VT for the differential gain. Alright, so I'm going to see if I can find an example problem here for us to look at in the next lesson. If I can't, we'll just move on to the small signal circuit analysis.